Let us see about three-phase fully controlled rectifier, that is a 6-pulse control rectifier. As we have seen already, a fully controlled rectifier consists of only thyristors and it is a three-phase converter. So you have 3 legs and each leg consists of 2 thyristors connected in series. And there is a method to number the thyristors. The upper devices are called positive group of thyristors, which are always numbered in odd numbers T1, T3 and T5. And this lower group of thyristors called the negative group are numbered in even numbers 4, 6, 2. So this is 1, 3, 5. Add 3 to this 1, you will get 4. Then add 3 plus 3 will give you 6. 5 plus 3 will give you 8. But you have only 6 thyristor. So 8 minus 6 will give you 2. So always follow this pattern while numbering the devices in 3-phase converters. Similar to a single-phase full bridge converter with RLE load, this 3-phase converter also has 2 modes of operation, namely a rectifier mode and an inverter mode. In rectifier mode, the average output voltage will be positive, whereas in inverter mode, the average output voltage will be negative. And in rectifier mode, power flows from AC source to load, and in inverter mode, power flows from this DC source to AC source. And in this bridge rectifier, at any time only 2 devices will conduct, one from the positive group, that is upper device, and one from the lower device, so that current always flows through the load. So to understand this 3-phase converter, you should know the difference between phase voltage and line voltage. So we know the phase voltage waveform VA, VB, VC is given by Vm sin omega t, and B phase is lagging by 120 degree and C phase is lagging A phase by 240 degree. Now let us draw the phasor diagram for this one. So this is VA, VB and VC. So the phase difference is 120 degree. So here it is 120, here 120 and here 120 degree. So what is line voltage? VAB is given by VA minus VB, and VBC is given by VB minus VC. VCA is VC minus VA. So now we will find what is VAB, BC and CA line voltage from this phasor diagram. So what is VAB? VA minus VB. So we have VA here, VB is here. We have to find what is minus VB. So what is minus VB? Just opposite of this one will be minus VB. So we will draw the opposite one also. So this is minus VA, minus VB and minus VC. Now we have to find VAB. So VA minus VB, you find the resultant of this one, which will give you VAB. So draw this parallelogram, you will get VAB. Similarly, we can do for VBC and VCA, and VC minus VA, VC minus VA is there. Draw the parallelogram, you will get VCA. So now this is VA, VAB is here. So what is the angle between these two? That is 30 degree. So VAB is, you can see the magnitude is higher. Actually it is root 3 times higher. Root 3 Vm sin omega t plus 30, because VAB is leading VA by 30 degree. We have taken this VA as reference because we have taken omega t here. So angle is 0 for VA. So writing everything with respect to VA. So VAB is leading VA by 30 degree. And if you take VBC, what is this angle? So what is this angle? It is actually 90 degree. So if you write VBC sin omega t minus 90 degree, because VA is here, it is lagging by 90 degree. And VCA, so VCA is here, so you have to find this angle. So till this it is 180 plus 30, so you will get 210 degree. So VCA is lagging by 210 degree. So you remember this one, VAB, VBC and VCA. So the other thing you have to remember is line voltage leads the phase voltage by 30 degree. That is, this angle is 30. So that we can draw the phasor diagram and the waveform, output voltage waveform. So let us see the working of this three-phase full bridge converter. So this diagram, I cannot draw it again and again. If it is in an exam, it will take more time and it is spacious also. So instead of that, this information in this diagram I am representing in a table. So here you have three phases A, B and C. So I have taken three phases A, B, C. T1 and T4 are connected to A. So write T1 and T4 to A. And T3 and T6 are connected in B phase, T5 and T2 in C phase. So in exam time it will be very useful. All the information here is available in this table. Okay. Now let us see how this works. So when T1 and T6 conducts, so which device is T1? It is here and T6 is here. So when T1 and T6 conducts, current flows through the load, then T6 is here, so current flows through this line. So this point is neutral. So this is the current flow path. So V0 will be, because this A is connected here and this B is connected here. So V0 is equal to VAB, that is equal to VA minus VB. So this VAB is the line voltage. VA and VB are phase voltages. Now we will see the how these devices are turned on in a sequence. At any time, two devices will conduct. So if you see here T1 and T6, and this will be in a sequence 6 1 1 2 2 3 3 4 4 5 5 6. Okay, but always start from this. You will understand the reason, because since I want to start from T1, I have taken this pair T6 and T1. So T6 T1 1 2 2 3 3 4 4 5 5 6. Now what will be the output voltage in each case? So when in previously we have seen that when T1 and T6 conducts, output voltage is VAB. So this is connected to 6 is connected to B phase and 1 is connected to A phase. So when T1 and T6 conducts, 1 is connected to A phase and 6 is connected to B phase. So output is VAB. Now when T1 and T2 conduct, T1 is in A phase, T2 is in C phase. Okay. So output will be VAC. When T2 and T3 conduct, so T2 is in C phase and T3 is in B phase. So BC is output. So how to write this one? First, always find the devices are connected to which phase. Okay. Then always write this first alphabet should be the upper device alphabet. And this one will be the lower device phase. Suppose you take T3 and T4. T3 is B phase, T4 is A phase. So BA. In T4 and T5, T4 is connected in A phase but it is a lower device. So T5 is the upper device. So CA will be your output. So if you know this sequence, it is easy to draw the waveform. You can blindly draw the waveform even without understanding what you are drawing. But you should know how to write this one. Only if you know this table, you can draw the waveform very easily for any firing angle. So what you can notice here is totally there are 6 devices and we have total angle as 360 degree. So 360 by 6 is 60. So each combination will conduct for 60 degree and each device will conduct for 120 degree. Okay. So each pair will conduct for 60 degree, each device will conduct for 120 degree. This is the phase voltage waveform which we have studied in the previous video itself, how to draw the phase voltage waveform. Now let us draw the line voltage waveform. So these are the line voltage equation. We can see that VAB, first thing magnitude is higher, root 3 times it is higher. Again it is leading by 30 degree, that is it is leading this voltage VA by 30 degree. It means that, what do you mean by leading? It is starting 30 degree before itself. So this waveform I am shifting to this point. That is, I am simply shifting this waveform to this minus 30 degree. Then you will get VAB waveform. So VAB starts here and you can find that here 0 crossing is at 180, here it will be at 150 because it has shifted 150 degree, 30 degree to the left side. Again VBC is minus 90 degree, it means that it is lagging by 90 degree. So this is VAB. If you draw the opposite of this, you will get VBA waveform. That is VB minus BA waveform. So VBC, it should start from 90 degree. Okay, draw the waveform. Then if you draw the opposite of this one, you will get VCB. Then VCA waveform, it should start at 210 degree because it is minus 210. So start the waveform from 210 degree and draw the opposite waveform, that will be VAC. Okay. So now hereafter we will use only this line voltage waveform, no need of this phase voltage waveform because your output depends upon this one. So in this video we will be analyzing the output voltage for alpha equal to 0, 60, 90 and 150 degree, 4 conditions. In 0 and 60 degree, your average output voltage will be positive. For 90 degree, you will get 0 and for 150 degree, you will get negative. So this is the condition where it acts as a rectifier. Here it acts as a inverter. Let us draw the waveform for alpha equal to 0 degree. Previously we have seen that in three-phase circuit when we draw the phase voltage 30 degree is taken as reference, but here we have drawn the line voltage. So always take reference as 60 degree when we draw the line voltage waveform. Now let us make this table, conduction table. First write this sequence T1, T6, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. So write this sequence, then find the time period. So I have told that 60 is taken as reference. So 60 plus alpha. So in this case alpha is 0. So 60, add 60 to it because each combination will conduct for 60 degree and each device will conduct for 120 degree. So 60, here you will get 120. So fill up the table. Now we can find that T1 start conduction at 60 degree. So you mark T1 here. So this represents the starting point or firing pulse for T1, and T2 is triggered at 120 degree. So T2 is triggered at 120, T3 at 180 you can see here, and T4 at 240 and T5 here, T6 here. You can see that all the upper devices are marked here, lower devices are marked here. Now you have to mark this conduction period for each device. So T1 starts conduction at 60 and it conducts for 120 degree. So 60 plus 120 is 180. So till 180 T1 conducts. Then T3. T3 conducts from this 180, add 120 to it, it is 300, or till T5 is conducted. Okay. Similarly, you fill up the remaining things, and you can, if you see this period till 60 degree, T5 and T6 are in conduction. During this period, T1, T6 are in conduction. During this period, 1, 2 are in conduction. Here, 2, 3 in conduction. Similarly, fill up these things. So, this is very important. If you write it correctly, you can draw the waveform correctly. Now, write this table which we have written earlier. So we have seen that when T1 and T6 pair conducts, output voltage will be VAB. So where is T1 and T6 combination? Here. That is 60 to this 120. T1 and T6 conducts, output voltage should be VAB. So now you trace this line VAB. Okay. Now when T1 and T2 conducts, output should be VAC. So T1 and T2 conducts from 120 to 180. So during this period, we have to follow VAC waveform. VAC is this blue color dotted line. So follow this waveform. Then when T2, T3 conducts, output voltage should be VBC. So follow VBC waveform. Actually it will be in sequence. So if you follow, you will get it directly. Okay, there is no difficulty in remembering all these things. Your waveform will come in the order only. So this is your output voltage. Next case, alpha equal to 60 degree. So same table, but alpha you substitute the value 60. So you will get 120 here and 180 there. Similarly, you fill up the remaining values. So T1 starts at 120 and this pair conducts till 180 degree. So T2 starts at 180 degree So similarly fill up everything. Okay, so now once you have filled up this one, you have to trace the output waveform. So how to do that? You see here T1 and T6 period. You take this one T1, so this period. Okay, so this period output should be VAB. So VAB is this brown waveform. So follow that waveform till this point. Okay, so this is your output waveform for this period. Okay, then T1 and T2 conduction VAC. So follow VAC waveform. VAC is this blue color dotted line. So follow that waveform. So now you have understood how you are getting this waveform. So fill up the remaining things, you will get this output. So this is the output when alpha is 60 degree. Now it is easy to draw the waveform for any firing angle if you follow this technique. Let us find the average output voltage for this case. So you might have seen that there are 6 pulses in one cycle. You can calculate in the output waveform 6 pulses are there. So in the total time period of 2 pi. And what are the limits? 60 plus alpha to 120 plus alpha. What is V naught? V naught in this case is line voltage. So to represent line voltage I have taken VML. Instead of VM I have taken added 1 L to represent that it is a line voltage. So simplify this one, you will get 3 VML by cos alpha. So these are the formulas to substitute and get this value. Next, let us consider the case for alpha equal to 90 degree. Same procedure. So fill up the details, all these details, do the calculation work and fill up these details. You will get the waveform like this. Now let me tell one example alone. Take T1 and T6. What should be output? VAB. So follow VAB waveform. Where is VAB waveform? This brown color. So T1 and T6 period is this to 210. Okay. So follow this waveform. Okay. So and till 210. So your output is like this. Okay. Now next you follow VAC waveform, then follow VBC waveform. So now it is simple. Next we will do for alpha equal to 150 degree. Okay. So fill up this thing. So this is the starting period for each device. Okay. So T1 starts at 210 degree only here. So now let me take one example T1 and T6. So T1 and T6 output should be VAB. So VAB is this brown color waveform. So where it starts? It starts at 210. So your waveform will start here and it follows till this point. Then again this point. So this is your output waveform. So if you know this table, you follow that line voltage waveform, you will get the output voltage waveform. Hope you have understood this one. If you have any difficulty in understanding or you have any doubts, you can give it on the comment section or you can email it directly so that I will answer your questions. So the points to remember here are, in three-phase circuit, when alpha is less than 90 degree, power flows from AC source to DC load. When alpha is greater than 90 degree, power flows from DC to AC, because we have seen that waveform itself lies in the negative side. So average voltage will be negative. But you have to remember that the direction of the current remains the same in both the cases. Current, because thyristor is a unidirectional device, current can flow only in one direction. So output current waveform will be in always positive, but voltage can change its direction. So these are some of the references. And if you like the video, do subscribe to our Read Electric Vehicle channel. Thank you.